Okay, good morning, everyone, and thanks for having me. So coffee, yes, it's an important thing that I like. In fact, it's kind of one of my codes in how I do stuff. So I'm going to talk about code today, but code as in often having curly brackets, but also code as in protocols of behavior, how we should interact. Because as we try to scale things up in the world, it becomes very important that we know how to have good codes, good protocols, good disciplines. And like, how do we cope in some cases? So if you travel a lot, how do you make coffee sometimes in places where coffee isn't very good? We have to often get creative. And so, for example, you might end up doing something like this. Like you're in a hotel room, particularly some hotels don't have kettles, and usually you've got an iron, so you can typically make coffee and kind of succeed in different places. But have you kind of noticed how many pieces of software we see, it's kind of a bit overly creative. It's people doing interesting individual things, but does that scale? Does that allow us to do things at a very large scale to really push forward and to drive to the next levels of doing stuff? Well, this year we took this photograph, which was kind of fascinating, the first ever black hole that was captured. And you may think, simple photograph, is it that easy? This photograph took 5 petabytes of data. It took 8 telescopes all around the world to put this together, including one of them was in Antarctica. And we could have had this 6 months earlier, but one of the protocols of being in Antarctica is you can't land aircraft there in the winter because the weather's so bad. And we couldn't ship this out over the internet because their network connection's not good enough. So the best way to get the data from Antarctica to the rest of the world would be analyzed was by shipping the hard drives. It was hundreds of kilos of hard drives to ship that. Now, that wasn't done by one person just doing something neat. Like 4 teams alone had to verify the software behind that. And it's building on the work of many individuals over many years and sort of applying good science, good engineering, great ways of working. So how do we scale to do that? How do we be able to scale up in any great endeavor to build things that are really, really big? So what I want to explore in this talk is how significant are protocols to development and how we do this at any sort of scale. Let's go back to what is a protocol. I often find that, especially in IT, we misname things a lot. I'm dyslexic, so I struggle a bit with words. I often look things up in the dictionary to see have we used the right terms for stuff. And I've been surprised at how terrible we are at this as an industry. Like, simple example, random access memory. That's everywhere. We use that term. Do we really want random access to memory? Like, just give us something random? No, I want something at a very specific location. I want arbitrary access memory. I think our industry is littered with these sorts of things, so we'll get around to this a bit. Like protocol, people may think Google protocol buffers. Well, actually, they're not a protocol at all either. It's another classic example of some of this stuff being misnamed. So what is a protocol? Well, it's a code prescribing a strict adherence to an etiquette and a precedent. So what we've got to deal with is ways of behavior, things that we're going to interact with. We must behave in a certain way. But for me, what's more important and often forgotten is the ordering, the precedence in which we do stuff. So I'm going to explore that a little bit this morning. The typical computer science way of describing it is more like this, where we're talking about the treatment and the formatting. We kind of obsess by the formatting and often completely forget the treatment. That's often where I find many of the causes of bugs in software, and we'll explore some of that later too. But let's go right back to begin with. Now, where is the origin of some of what we look at for protocols? Well, it goes right back to evolutionary biology. We're hardwired to do certain things. Charles Darwin did a lot of work on evolution, and we got to know a lot about that from some of his work where sort of Darwin and Wallace produced on that. One of the other areas that Darwin also did some work on was behaviors and how people interacted. He discovered and documented how we have certain patterns of behaviors as individuals that it's not a learned instinct, it's actually inherent in us. For example, when it comes to communication, all around the planet, we know how to sort of express disgust, we know how to express joy, we know how to express shame. And this has been proven by even looking at people who are blind, who have never seen those, by kids who haven't yet been exposed to stuff, and people who've even had unfortunate feral upbringings and weren't taught any of this stuff. So it's actually in us. This is kind of instinctual at many levels. So we explore this to see how this has evolved over time. So like, this facial expression side is important. It also drives a lot of our behaviors. This has evolved into manners and etiquette, which is a little bit of the title of the talk. So we have manners, ways of behaving, or etiquette of behaving individuals. Like the term etiquette is an old French word. It was coined around the time of Louis XIV. It means little card. Whenever you were at the Palace of Versailles, little cards were passed out to the diplomats, like, don't step on the grass. Like, we've all seen some of this stuff before. That's where it comes from. It tells us how to behave, the things that we should be doing, ways of thinking about stuff. But manners is kind of really interesting subject. It's split into 3 levels. At the first level, we talk about the hygiene manners. This is where we sort of exhibit things like disgust. And the whole point of this is to stop the prevention of disease. So as individuals, we kind of learn to sort of go, ooh, that's not very nice. Stay away from that. It kind of keeps us away from things. It stops us catching things in the first place and also helping stop the spread of diseases. At a software level, think of this like encapsulation. We want to encapsulate something, so we've got a very clear interaction with it. I like to bring it back to the disgust point of view. I think in IT, we haven't expressed disgust enough. Some of our basic internal instincts. I've worked on many projects and done a lot of things with JavaScript at different times in the past, and I felt extreme disgust. Maybe we should have stopped the spread of some of that disease earlier on, and we'd be better off as a community. So they're thinking about some of these things. So some languages are better than others. Some ways of working are better than others. We should sort of tap into our sort of more basic instincts. The next level up from this is courtesy. And courtesy is about how we make society start to scale and function at a larger level. It's going beyond the individual. So in courtesy, we let someone else go first, like someone else eat first, or we take turns at things. And by showing courtesy, we're showing that us as an individual is not as important as the whole group. And so we get to expand and go like that. And think about how that works. Basic societies often break themselves down into people who farm, people who are the warriors, people who are the communicators, these various different roles in society. It would be very easy for the warriors to take all of the food and take complete control. But it's not sustainable. You wouldn't have food after a while. So behavior-wise, we have to work together and show the courtesies. And kind of an interesting question about if you have a bonus scheme at work and it's individual related bonuses, you're actually going against nature in many ways. And I wonder why some of the teams fail to work and don't scale very well. The last level to this is norms. And this is where we normalize our behavior and we try to do things in standard ways. This builds trust, and trust makes us more efficient. And so we see these things, and we see this right through lots of societies. It's a well-studied and fascinating subject. But we can get a lot from that as well. So this is why, especially when you get to levels of scale, we need to normalize what we do. It builds those efficiencies and we can start doing things better. This can get really formal in some ways. The most formal examples I've sort of found in studying this subject is things like our international laws particularly, and how we go to war is one really good example of this. So in the military, they talk about rules of engagement. And there's a body of law formally deciding how we should behave and what we should do in these sorts of things. Fundamentally, the question to be answered is what is acceptable? Because war is a horrible thing. People die. Things go really badly wrong. We have a very distinct view in international law that if you follow the laws that are laid out, you're considered a soldier. If you don't follow the law, you're considered a murderer. And it's that simple at many levels. I got to see General Mike Jackson at a conference I was at a number of years ago. Kind of fascinating individual. He was a general in the British Army, served all around the world. And he talked about how warfare is conducted. And it's kind of interesting how he presented it. He says, the whole point of war is not to crush your opponent. It's to change their mind. The whole thing is to change a point of view. And it's an absolute last resort. How he talked about how he engaged was just amazing, and particularly how to manage people and how to direct people and do things at scale. Like these errors are very mature and well followed. We see discipline examples all around the world. Like the laws that are behind that are just ad bello, and that means the right to go to war and to perform war rightly. So for example, you can't just go to war. If someone attacks you, you should have a proportional response. For example, if someone was to sink one of your ships, a proportional response would be to do something similar to try and change their mind that that's a bad idea going forward. If you're a superpower, you wouldn't just go and do a nuclear strike on their capital because they sank one of your ships. That would be a war crime. And so it's kind of interesting how this goes. So that's the kind of formal, interesting background. We'll try and weave some of this into how we can apply this in computing. Because when I talk about concurrent distributed systems, I'm sure most people here build these sorts of things all the time and fundamentally want to answer the question, how should our components interact? Because this will let us scale our systems. This will let us do stuff safely, more efficiently, at a larger sort of scale of doing stuff. Now, people often ask, how do I find out about this stuff? Where do I learn? Well, one of the bodies of work we have out there where we get to understand this is the IETF. Lots of protocols are documented. It's fundamentally how the internet works, is backed up by a lot of these. Some of them are quite good fun. We produced RFCs, and when the RFCs are published, they cover different protocols. On the 1st of April each year, there's a really interesting RFC comes out. So one of the examples was the hypertext coffee pot protocol. So we can control a coffee pot by hypertext. And this came out in 1998. I love the things like up on the right-hand side, you'll see errata exists. So it has been corrected over time. And what's really cool is these are some good examples to get a flavor of how to write a document protocol, but it's also quite good fun. Like, particularly if you dig into that, you'll find there's a return code for the protocol, and that's 418 formally defined, and that means I'm a teapot, I'm not a coffee pot. So you can't use this protocol with me. Some of them even really help explain some of the background for our subject. This is one of my favorites here, Holy Wars and Plea for Peace. And what they're talking about is big endian and little endian encoding. So if we've seen our integers, what we're talking about is which byte, which bit travels first whenever we start to transmit stuff. So we talk about the encoding of things. The history of that word, which is explained in this paper, is down to Gulliver's Travels and Lilliput. And what we were discovering is there was two tribes, and the tribes went to war over how you eat your eggs. Do you eat the egg by the big end first or the little end first? And that's big endian and little endian. And that's the history of some of this. But this paper is like hilariously funny, but also really, really informative. You want to know the history of how we encode integers and how we transmit integers on networks. Like other examples are how to transmit over avian carriers, pigeon post. So that's going back to 1990. Later on, we updated that for having quality of service in 1999, and most recently, we brought it up to date with IPv6. So the kind of sort of fun stuff, this is places where we can go and learn and sort of get to find out about these things. So that's one example of how we document them. Like, how else should we on a project? Where do we start? How do we make this relatively simple? Well, this question I find that most people fundamentally don't consider is that there's a difference between an API and a protocol. And they are very different. I think an API is a very two-dimensional, quite flat view of how to interact with any component. And it'll talk about the behaviors in some ways because it lists the things that we can do. But remember back to the start, and it says one of the other important things is the precedence. It is the order in which we interact with something. APIs don't tell you that. You might find it littered somewhere in the documentation. You got to call this method before you call this method. But it's really important that we express that. A simple example of this. So let's say I have a file protocol and I want to interact with a file. Well, we can express it in a kind of pseudo-regular expression style syntax. This is one I've been doing for some time, and I've discovered lots of other people have kind of simultaneously discovered this same approach to doing it. There's various other ways of doing it, EDNF and other forms that have been around longer. But I find this is quite easy to read and easy to deal with. So for a file, I can open a file. I can then perform 0 or more read or write operations in any order, and then I can close a file. So now I've got a clear expression of what is the precedence with which I can interact. Like, I can't read or write from a file until I've opened it. So it becomes pretty simple as a way of thinking about it. Then we just document what are the methods, how to do them. This is a great way to start into the design for any component that's going to interact with another component, forms the contract for how we interact, makes it easy to understand how you're going to deal with something without having to dig into the code. I can get more complex. So I work on a messaging system called Aaron, and we have various protocols for how we interact on the network. This is slightly more complicated. So like, how do we do a connect? How do we manage flow control? How do we do loss recovery? How do we measure round trip time? What are the messages that can go? And you show that you can get an interaction between sender and receiver. We have this on a wiki if you want to sort of dig into it in more detail, but it starts to give you an idea that it's quite simple at some levels where you try to sort of dig into lots of dense text. It becomes more difficult to do this. But as we start looking at this, what's the big thing to watch out for? This question, I think, is really, really important. We see this makes many systems very fragile. I liked how Kant pointed this out in the last session, where we often don't think about what can go wrong and get rewarded for it in the right way. Yet it is so important, especially when we're building software. Some of our protocols, our ways of approaching this, we don't answer this question. I get to work with this guy most of the days that I'm writing code, and he used to work for NASA. And he used to always ask me this question quite often early on. And I started to really appreciate the importance of it the more you sort of start doing it. And his answer to like why he does this a lot was really quite simple. When you knew an astronaut was going to die, if you got certain conditions you didn't think about, you took it seriously because someone else's life was in his hands because he was writing software and verifying software that needed to do that. But most of us say, oh, well, what we do doesn't really matter. It's not that important. People's lives aren't at stake. Possibly yes and possibly no. Like a really good example in the UK of this is we built a patient health record system. The government spent £12 billion on this system and it failed to deliver and didn't work. Like, that's software. Does it matter about that? It's just software. Well, that's £12 billion that didn't go into MRI scanners, cancer treatments, various other things. So yes, people did die as a result of some of our crappy software and inability to deliver projects. So if we were better at this, it does sort of get better. This paper is really worth a read if you haven't seen it. And what it talks about is what are the causes of P1 outages in production systems. When we got a production system, they investigated the causes of P1 outages where the whole system stopped. And there was loads of various findings in this that were really interesting. One of my favorites in it was 25% of the P1 outages were caused by unhandled error conditions. Exceptions being thrown, return codes coming back. They identified an error. It wasn't a complete surprise. It was unhandled. In many of the exception cat blocks, those to-do statements found, I need to fix this before it goes into production. Is that a protocol for our way of working for delivering software that's reasonable? Rather than get it out, get it working, but not thinking about what can possibly go wrong. It really sets us aside becoming more professional as an industry, how to do things. I like to kind of think of it a bit like we go back to being medics or doctors 150 years ago, where there was arguments about, do we wash our hands before performing surgery? Surgeons used to argue about that sort of thing. Florence Nightingale pointed out by using pie chart for demonstrating the percentages of patients who died through infections afterwards when doctors didn't wash their hands versus when they did wash their hands. So we kind of got to learn some of these things. Maybe our industry will take some time and we'll eventually get around to getting more professional, having some disciplines to do that sort of things. So let's look at another example of protocol and how we can approach things, because how we interact at scale becomes really interesting. And it's not about just the individual component, it's how many components interact. So imagine we have a system and we're going to send data out to lots of clients that are going to consume the data. The classic problem for this would be market data if you're in finance. It could be a chat server sending out to multiple people scenes of video surveying, all sorts of interesting things where you're broadcasting data out to lots and lots of clients that get to see this, an interactive whiteboard, something similar. Now, we can do this over the likes of TCP. And with TCP, we send the data out to everyone, and there may be loss. Data may go missing as we're transmitting this out. How do we then make sure we cope with that loss and scale up in some sort of way? Well, TCP sends back an acknowledgement for all data that's sent out. So as you scale up the number of clients, you're having trouble scaling with just the multiple times you're sending, and then you're trying to scale with the multiple acknowledgements coming back. This just doesn't scale up. It becomes impractical at any sort of level. So multicast with IP multicast is an obvious way to start making this better. It solves the transmission problem out of the data, because the same data gets sent to everybody, and it's sent once from the source, so the source doesn't have a scaling problem. We federate out the problem through the network, switches and hardware, lets it scale out. But what if data goes missing? How do we report that the data's gone missing? We can't send the ACK back again because we get the same problem as TCP. We need a different solution. Well, early multicast approaches to that used to do negative-based acknowledgements. This is a pretty standard technique. So you send a NAC, if you lose the data, and then you get it sent again. So this does scale a little bit better until you start to realize that most NACs are correlated with the source being the problem for it. So for example, you go to send out data, the nearest network switch, the nearest router, maybe the OS that actually sent out the thing, filled this buffer, it starts dropping packets now. So the source is sent it once, it doesn't make it to all of the receivers. As a result, we get loss everywhere. Now, if all the receivers then send a negative acknowledgement, you get a storm of negative acknowledgements back to the source, and your network starts to degrade really badly. And this becomes known as ACK or NAC implosion. So it doesn't scale. Well, how is this addressed? How do we come up with a better way of dealing with it? Well, this particular paper was one of the breakthroughs in there, where we had a means of sending back NACs, but in a more managed way of scale. How can we treat all of the servers like a society or community, and they all behave and collaborate? Now, some people started experimenting with techniques whereby they nominate someone to take control, and this is kind of classic command and control type thinking. This paper turned it completely on its head. It had the idea that whenever you go to NAC, you don't just send your NAC straight away. When you realize you've lost some data, you set a random timer, and you set it for quite a short period of time into the future, typically related to the round-trip time between the source and the client. And this random timer would have an interesting distribution that some will go off sooner than others. So all the clients are doing this. The first one to have their timer go off, they send the NAC. It goes to the source retransmits the data. The others, as their NACs go off, they check to see has the data been retransmitted, and if it has been retransmitted, they don't need to send a NAC. So no command and control. It's a central organized protocol rather than a central coordinator in this as a system. Actually turned out to scale beautifully. I know about this scale beautifully because it's actually implemented, and it does work really, really well. It was kind of excellent in how it works. Now, what's fascinating is if you look at the first name on that paper, first name on that paper is a woman called Flawed. Now, Flawed, brilliant physicist, brilliant computer scientist, but what's fascinating to me about her is her first degree was in sociology. It took a sociologist to come up with that sort of algorithm that the physicists and the computer scientists all didn't come up with. Somebody who thinks differently and thought about how does society scale? How do large communities scale? You don't scale them by command and control. You scale them by protocols of how they interact. Like we see this with sort of ants and termites and all sorts of other interesting insects. So simple protocols to how you interact can scale really, really nicely. And this was a great breakthrough. What it did was it would done the random distribution just as a standard distribution. So you still had a bit of a problem where some of the things would all come around the midpoint and you could still have some interesting issues on scaling. This paper took it a little bit further forward. How about rather than having a standard distribution, we'll have an exponentially distributed distribution where we'll scale towards the back end, but we'll chop off enough of the front of it so the probability is quite high of a NAC coming out relatively soon. And we've guaranteed that we'll get them all by the end anyway. And this turned out to scale even better and be even more efficient. So again, like no central control, using math, using probabilities was a really nice way of making some of this stuff work. It scales up really, really nicely. So if you want to get into protocols, where should you focus? What to learn? How do you even start? Because there's many subjects within protocols. Like I'm just sort of listing some of the topics that are kind of interesting. I'm going to pick off a few of them and kind of explore them a little bit here, not for this part of the talk. So I'm going to start off with, who cares about waste? Probably most people in finance don't really. We just love to waste stuff, don't we? It's kind of, well, if you like JavaScript, if you like text-based protocols particularly, I get to measure lots of real-world systems. And so often the business logic is just a rounding error in the amount of CPU time being used. The majority of it is spent in typically creating text-based protocols, which are deeply inefficient, like JSON, XML, whatever. And like, as a society, we have moved forward from XML to JSON. So we had type information and we threw it away and got JSON instead. Where was the disgust? Why did people not just start expressing disgust at how we went so badly wrong? And our binary protocols are much richer. They're much stronger type checking. They're much nicer ways of doing stuff. What we find is, I usually get this as a response, but it's human readable. This is the kind of like the crybaby approach to it. It's like, it's not human readable. I only know I work in protocols and I only know a handful of people on the planet who can read ASCII, like genuinely read ASCII. And I know nobody who can read UTF-8. So it's not human readable. You have an editor that lets you read it. So we have tooling. We just need better tooling for our binary protocols, and there's lots we can do to make this better. So like, we're attributing the problem in the wrong place, and that leads us the wrong way on many of these sorts of things. And if you start doing binary protocols, you can start to do fun things. Like if you want to get creative, you can do ASCII art, and this is one of mine from a protocol I worked on, where you express things, but we can then build stuff to read this stuff and make it work really well. If you want examples of which protocols are out there that are very inefficient, so things like SBE, Flop, Buff, Cap, Brutto, SM1, there's quite a few of them out there. And they're not a percentage point faster than some of the others. They are orders of magnitude. Like SBE is 3 orders of magnitude typically faster than Google protocol buffers, usually 4 orders of magnitude better than running JSON. Like orders of magnitude, is the level of waste is incredible. To put this in context, we spend more energy globally now in our data centers than the airline industry does. And it's increasing at a rapid rate. The ITRS report from 2015 says we continue on our current trajectory. By 2040, there will not be enough energy production on the planet to power our data centers. And that includes our increases and getting better at energy production. So this whole thing about we'll throw hardware at the problem, it ain't going to fly much longer. But unfortunately, we've had decades of Moore's Law and things getting faster and better all the time, but that's stopped. It has come to an end. So we got to think about different things. So that's kind of my ranty bit. I'll move on from that. Let's talk about versioning. Versioning is a fascinating subject that we often don't dig into enough. Like at top level, we want to version our protocols. So we want to know what conversations we're actually having. So what are the valid words we're allowed to use? What are the valid verbs in our conversations to have that we can add new things in? So our conversations should always go forward. They should be extensible. So you can have conversation with someone who is less sort of experienced. That's fine. So think of just like normal life. You can have a larger vocabulary than some of the people you know. Still means you can have a conversation with other people as well. You may not just have as rich a conversation. And so building our systems to do that. Society does that very well. We also need to cover like, how are we encoding our messages? Like, can we add new fields to the thing and be backwards compatible? The important thing is we always should be backwards compatible. So we add by extension. Extensions are optional, so we can continue to have conversations. We may do richer conversations later, and when everybody's moved on to the same level, we can then start deprecating and moving on. But there's nice ways and approaches to doing this. The really interesting one for me, and something I'm getting to appreciate more and more, is how we version instances and version state itself, which is often not done. We start to see the various levels. So one example is, like, if you're going to do consensus algorithms, the RAF paper is a good example of this. Is like we version the state of the system. So we version every election. So every time we have an election for a new server, we give it a new version number. So if you get a message from a previous election, you know, this doesn't apply in the current one, we just throw it away. It's fine, it won't do any harm. If you don't put a version number on it, you've got problems, because you'll end up with a double counted vote. In some cases, that becomes a real problem. But we can go further. So I've spent a lot of time working on various types of queuing systems, various concurrent data structures, and producing multi-producer, multi-consumer queues is a kind of fascinating problem that many people have studied. And to do this well, particularly without locks, there's a number of implementations. Some rely on garbage collectors, some rely on other techniques. I've done some myself and found that the edge cases get incredibly complicated to deal with them. And then I started to do lots of research around this and find most of it's actually quite poor until I came across this site, 1024code.net, the work of Dmitry Yukov, which wasn't that well publicized. It wasn't through most of the academic research. He used to be at Intel. He's now at Google working on the Go language. And in the first weeks, he made Go so much faster than it was previously. But in reading his algorithms, what stood out for me was he solved the multi-producer, multi-consumer problem in a really elegant way. And I remember reading it, and it wasn't like, oh, I need to scratch my head and understand it. I read it once and went, wow, that's right. And the reason it was so clear to us, right, is he versioned all state. You could see how all the edge cases were handled. It was just obvious. And by actually thinking about, I'm going to version everything. And there's actually quite an elegant, simple algorithm. He got rid of a lot of the complexity because it was versioned, where people would say, oh, adding the versioning to every state change in it would have made it overhead, would have made it more difficult. Yes, it did add a little bit of overhead, but that overhead completely eradicated all the complicated edge cases, and so more than paid for itself in an interesting way. So we get some really nice, beautiful examples of this. Async versus sync. This is a debate that goes on so much in our industry. I think the internet has broken how we do software in a really big way. I started using, not so much the internet. The internet's really cool. So the web is actually the problem here. So I've been doing the internet before the web came along and existed. And whenever the web came along, we use HTTP and everything is document fetching. Our programming models are now based on document fetching for everything. It seems to be what we do. So if you were involved with the computing world before the advent of the web, you probably get a very different view than the people who are involved afterwards. What we end up with is sort of idea that everything must be synchronous. So we send a request, we expect an instant response. And so if we send a request, we get a response back. We send a request, get a response. This is kind of the typical interaction. But notice how time is passing as we're going forward doing these things. If I increase the latency, so it's going to take longer to send a request and get a response. Notice how I can't get through my 3 requests that I previously had because I don't have enough time. This becomes a real problem. And what's happening whilst we're waiting? We end up suspending a thread that sent the request. We have to put it asleep. We have to wait for to get a response. They've got to wake it up again. We get the operating system involved. And this is like getting lawyers involved to have a simple interaction. The overhead is massive. Most people don't profile. They don't know the relative costs of these things. If you run a profiler, you start to see how many millions of CPU cycles are wasted on doing some of this stuff. And also the code ends up very tied to being threads on stacks, doesn't really scale. A lot of the problem with this is Google produced a paper a number of years ago saying we should scale using threads. The paper was fundamentally flawed, yet it spread around the internet like wildfire, and everyone, because it's from Google, that's right. And not always the case. You need to do the research. We need to have independently verified science to do this well. Now, let's say it's asynchronous. Is it different? So we send a request. send another request, send another request. Notice I'm not waiting for responses, but then the responses start to come back. So they go in a different fashion. If I increase the latency, what does this do to time? Notice how the impact of latency is much less once you start going asynchronous with a very different view of the world. And then you're into this world of, well, what's happening in this case? Well, you send, and you check for responses using non-blocking APIs. But you don't have to be suspended by the operating system. You can go off and do something else. It's perfectly valid. You can do other work rather than working. And doing this well, like one of the ways of programming is to move to state machines. It makes our life so much easier in space. But again, it's one of those long-forgotten ways of working. I get to teach concurrency. I teach protocols, networking, all this thing. I've started to see some patterns in who's good at it and who's not good at it. One example of things that if people have as a background tend to do much better at this is people who are good at cooking. And if you think about it, if you want to cook a complex meal in the kitchen, you're trying to do multiple things concurrently, multiple things in parallel, and you're trying to coordinate with timing. It's exactly the sort of problem. I can look at someone's commit history and tell whether they're probably going to be a good concurrent programmer or not. If you work with lots of small, tiny commits, small steps, good rapid feedback cycles, you tend to be quite good at this. If you're the sort of person who creates a huge feature branch, goes off for months, and then tries to merge it back with everybody else and merge conflict hell, you're probably not going to be good at this. So it's kind of interesting. These things show up, and these are protocols of behavior happening at all sorts of levels of skill. It's fractal. But again, you get these people crying again, but synchronous is so much easier. They're like the people who cry about tax-based stuff. It's like, go learn something different. Some of the stuff that we do is hard. Kind of suck it up. Get good at it. But it pays off in the end. It gets to be much better. Like, we're not in this sort of world, but the synchronous is blocking. So we've got to just consider that, and we work with it. And it's all about how we manage the feedback, because we're constantly getting feedback. Like, the math behind everything that we do is about getting our feedback cycle short, so get used to managing it. Like, we've got to build our APIs that way, we've got to build our protocols that way, so we're getting the constant feedback. Like, we have lots of research that shows this and proves it. Even back to the Claude Shannon in the 1940s proved it mathematically, the importance of feedback and how we do this. We've got to go forward. But if you've got crybabies in your team, it takes a little bit while. Build an async protocol, an async API, wrap it with asynchronous, so put training wheels on, and so keep people kind of happy, and eventually we'll move them over to doing sort of the grown-up way of working, and we can move forward. Like, do our network people know about these things? Is it a problem? Well, yeah. So we've been doing RPC for ages, doing it badly. Every generation has another go at it. They run into the same wall, hit the same problems, and then they stop doing it, and then another generation forgets it and tries it again later. I've seen this come around 3 times so far, and we get to see underneath how protocols are evolving to try and cope with this silliness that people are doing above. So like TCP had to be extended to support fast open, because if you're making request response all of the time, the sort of HTTP type interactions, setting up the connections expensive. So we go to fast open. We've now got quick being used. So if you've got a Google service running in like Chrome, if you're using sort of Gmail, Docs, or anything like that, and you're talking to the Google backend, you're not using TCP. You're using UDP with a protocol called Quick over the top of it, because it gives us a much more efficient interaction. We've seen this with HTTP1. We went through Speedy to HTTP2, where we got rid of all the tax-based stuff that we used to do. We're now in binary, using HPAC and other efficient ways of working. But we make mistakes. Somebody didn't ask the fundamental question, what can go wrong? So now we've got HTTP3 coming, because in HTTP2, no one sort of thought, what if one of my connections gets jammed up and we get headline blocking, which network folks know about, but the people at the high level protocols didn't. You end up with a page that doesn't render progressively. So we're trying to fix that now in HTTP3. And we're adding these things. We see various things at TLS, moving to TLS 1.3, where it got a lot faster. So TLS 1.3 is one of the more comprehensive documents that have been produced in the IETF. Great learnings in this. And I think some of the things that really stood out for me was how we optimized stuff and we didn't consider what many end users do. So for example, TLS 1.3 allows for a much faster connection setup. It does this zero round trip by remembering some of the previous state. Well, this makes us vulnerable to replay attacks. It wouldn't have mattered if people who are designing protocols at the higher level, they're building on this below. And for example, if you had a sequence number in every one of your messages, if you had versioned the instances of doing things, you wouldn't be subject to replay attacks. But most people don't build protocols and think about these things. So if you put a correlation ID that's monotonic into all of your interactions, you're safe from this sort of stuff. So we can build up on that. Batching is another interesting one. So let's consider the etiquette of a request. So from a human behavior perspective, you go round to a friend's house and you're going to have dinner and you arrive at their house and they say, you know what, I need some milk. Could you please go to the shop for me and get some milk? And your friends, so you say, no problem, I'll go to the shop, I buy the milk, come back again. You come back and they say, do you know what, I actually need more milk. Could you go back to the shop again and go get that? So you go, okay, I'll go back to the shop again. You come back again and they say, do you know what, I need more milk and I need some cheese. And you say, hang on, I'm going back to the shop again. I'm supposed to be over at a friend's house, having dinner, having good conversation, sort of hanging out with them, but instead they keep sending me backwards and forwards. Your friends wouldn't do that. Like our natural wiring, we will think about these things, we'll batch them up, we'll try and do them efficiently. But notice how we deal with computers. We don't think about them. We don't think about them in any way showing any consideration. They're kind of inanimate. They've got no feelings. It doesn't matter. Their own instincts is like, we do think about things. In fact, whenever humans try to do horrible stuff to each other, they deliberately dehumanize. So they try to take away some of our hard-built wiring. But I'm not saying the computers are nice and we should think about them, they're all kind of fluffy. Although whenever they do become sentient, I'm hoping because I'm one of the nicer people to them, they don't come after me. Maybe they'll come after all those people who made them process lots of JSON and done nasty things with synchronous requests and get us all that way. But so just think of, so this was the origin of whenever I'd done the mechanical sympathy blog. It come about from Jackie Stewart's ideas of motor racing. Having sympathy for the vehicle, you can get much more out of it. It's exactly the same with our hardware and our OS patterns. Because it really starts to matter. We're now moving into 100 gigabit Ethernet. And the BSD sockets API can't push 100 gigabit Ethernet. It's just not possible. The overhead of the system causing the synchronous nature of dealing with it is we can't make that number of requests per second to drive the packet rates to make this happen. So we're having to revisit these APIs to make it work. Like on Linux, we start to see send a message, receive a message. Batching has to become a natural way of working. We need to reduce the overhead of making individual calls so we can't have the bureaucracy of locks and going into the kernel. We need a much lighter weight protocol way of doing that. And we're seeing that with like sort of DPDK, EFI, unload, various other techniques in that area. So we need to be aware of this, and this lets us go forward. So one kind of final little diversion on this before I wrap up is, but we also have lots of other protocols that are incredibly popular that I kind of call them our snake oil protocols. And this is usually because vendors are preying on people's human behaviors. Like we like to be told that all our problems can be taken away. We don't need to care about certain things. We buy their product and silver bullet takes away everything. One good example of this is two-phase commit and exe. Perfect example of a snake oil protocol for me. It's like you have distributed systems, coordinated transactions will take all their problems away and you don't need to care about them. It's lies. It's seriously flawed, this protocol. It's been formally proven to be incorrect. Again, that hasn't spread anywhere near as fast as the fact that most corporations are doing it. In fact, actually, most architects in large organizations love these sorts of protocols because they then get to push down all of the problems to the vendor rather than owning up their own responsibilities in this. One of my favorite papers is this one, talking about how this protocol is so broken from consensus perspective. And if you don't know who Jim Gray or Leslie Lamport are, you're kind of missing two of the greats of our industry who kind of really understand this stuff. And they point out quite simply, two-phase commit is just fundamentally flawed because if you get a fault, you have no fault tolerance at all in the system. It should be consensus-based. There's much better protocols for doing this sort of thing. So this is typically the sort of things that you get. So kind of question what you hear sometimes, particularly from large vendors, One of my favorites is people who say they can do guaranteed delivery, trademark at the end of it. Again, it's a complete lie. We can pretty much give, and most messaging systems, you can do at least once delivery or at most once delivery. The exactly once delivery is not possible. It's just not mathematically possible in doing it. Yet we kind of see people promising this sort of stuff. But if we take the right responsibility for actions, we can make these systems work really quite well. Because again, it comes down to the feedback. It's an application level needs to know what it's sent, it needs to know what its responses are, and start versioning state. Then a lot of these problems go away. You can't just push them down into the stack below. So kind of know what's in the stack below and know what you can depend on. So let's wrap up here a little bit. Like, how significant are protocols to software development? So thinking about how this goes ahead. What's this protocol? Anybody recognize it? Yay! Scientific method, probably one of the most important protocols humans have ever come up with. And particularly I like this part of it, falsifiability. So let's give a good example of this. How does it stack up? So imagine someone reports a bug in your system, and you're going to go fix the bug. Now you could fix the bug, and then you could write a test afterwards to show that the bug has been fixed. Is that the scientific method way of approaching it? If you truly do tests first, what you do is you write the test that shows the bug and illustrates it. You have falsified that the system meets its requirements. It doesn't. It's broken. The test illustrates that, and you see the test fail, so you know the test is correct. Then you fix the bug, system now passes it. So just thinking about the protocol, thinking about the approach, that's science, that's a bit more professional. That's a protocol how we should go about doing some of these things. And Conway's law starts to point us out at all sorts of levels. So Conway's law, for those who don't know, says that any system takes on the shape of the organization communication structure that built it. So teams that are organized into a way that have good communication, good protocols, good ways of interacting, it tends to reflect in the software. And vice versa, that if you have teams that don't function very well, we end up with those problems and it doesn't scale and work and has all sorts of brittle properties. It's been shown that if you actually target the team to be working in the right sort of way and thinking in the right sort of way, you get software that does that. And so it can be used for both ways. So it's really worth considering what are our protocols, how do we scale? And it's fundamentally about how do we interact at the end of it. And on that, I'll thank you very much.
Any questions? Probably I'll start with one.
Sure.
So going back to the protocol that you talked about, especially when it comes to multicast, how big should the system be, or how many nodes should the system have in order to show performance benefits, or how small? I mean, let's say I have a 3-node cluster. That's my first part of my question.
Yeah.
And the second part is, you also talked about encoding, and especially if you have nodes that are saving data down, let's say in terms of a cache, which is holding data in its memory. So having a binary encoding format for that as compared to text, what's the performance benefit?
Okay, so the first question, excellent one, is if you take a protocol like was done with the multicast, so you've got NAC, but you've got NAC in a coordinated way by using the random timers. Where is the sort of cutoff points for it? Well, you start to see significant benefits once you get into the high tens and going beyond that. It really starts to show there. When you're down at single digits, it does provide benefits at all the levels. Like once you're actually beyond 2, it starts to show, but it's not as pronounced. And the cost impact of it going wrong goes up significantly. It's an exponential effect. So you see it at lower levels and gets much more amplified at the higher levels. It's like we see these sort of things in human teams, like a team of around 5 to 7 can communicate really well and compensate for being imperfect and some of those other things. Once you start going beyond that, you need to split into separate teams and have different protocols of interaction at that stage. And we get it's an efficiency thing, but it actually becomes a point that beyond a few tens, it becomes something that you're spending so much time in the catastrophic cases. I've seen systems that are less than 100 totally fail whenever they got into NAC implosion. So you need to do it at the tens level. at the individual digit level, you can cope, you don't get to see these things, but it still has benefits at that sort of thing. And this is also part of our testing problem is people often test with small numbers, and so they don't see these, but at the higher stuff. The question on the encoding, was it, were you asking about the relative costs of?
That's right. If I have, let's say my use case is a clustered setup. I have multiple nodes, and it's essentially a cache so that I don't have to go to the database constantly. And it is a distributed cache system. And in that case, would the encoding, decoding would be an overhead when I'm trying to just read from the cache? Or would it be more sensible for me to save it as a text UTF-8?
Yeah, so good. So if you want to encode and decode in, so some of the best binary protocols, their encoding and decoding cost is actually very similar to reading fields out of structure or fields from a class. They're good. SBE, one of the protocols are one of the encodings I work on. We can encode or decode market data messages in about 15 nanoseconds or less, depending on the speed of your CPU. If you're going to use something like JSON or whatever, you're talking at around 10 microseconds. So like 3 orders of magnitude difference. And you start looking at things, well, if you've got a system that's running at 1 million events per second, and not everybody does, but some people do, you can't have an encoding that takes more than a microsecond because you just spent your entire budget on encoding rather than doing the actual work. And so you get to see this. The interesting cost I've seen played a lot, because you talk about the startup cost there, people often will think about, okay, what's the cost of my running system? Like, so how fast do I need to make that? And one thing they often don't think is, what's the cost to start a system? Because if you want a highly available system, there's 2 parts that are really important. One is the mean time between failures. So how long will you run before you see a major failure? And you can have fault tolerance, you can have redundant machines, various things will increase the time before. But you have to accept that you also will have a failure that you haven't thought about. The system gets so complex, they will ultimately fail, even when you've got high availability. And also, they're going to fail at other times because you're just going to restart them. You're going to add new software. You're not going to think of how to make it perfectly upgradable. Then it's the mean time to recovery, and that's the startup time. And that's actually one of the horrible times I've seen people under pressure waiting for the system to start, and it takes too long. Where if the restart, if the thing can go wrong and you can get it up again and going really quickly, the impact of being wrong is not that bad then. So that's an area I often encourage people to think a little bit more about performance because they just forget it. They don't see it. They'll measure the cost when it's running, not the cost to start up or restart. Cool. Gregor's got one. I think it's going to be the last question because we're at time.
So I really like your comment about that an API description is really 2-dimensional and totally flat because it basically ignores all the things you just talked about. On the other hand, every time somebody has tried to fix that, like I remember the old XML SOAP days, there was like service interaction protocols, like every time somebody has tried to add this to interface definitions, it hasn't seen a lot of uptake really. So I was curious, like how do we fix that? How do we make it easier for people to work this into APIs or think about this stuff?
Yeah. Excellent question. So hasn't had a lot of uptake, take context in this. If they have a lot of uptake, your context is the corporate world, you're absolutely correct. If your context is network and infrastructure, not the case at all. The IETF have loads of examples of this. Like our networks that are running around the globe are based upon a lot of this stuff, and it's working. The thing is, it works so well we don't even notice. That's a kind of interesting thing. This stuff is so good you don't notice, yet we spend so much time dealing with the poor side of the corporate world. And I think actually some of this comes down to the crybaby-ishness. The corporate world is set up for often what the goal of the business is, not for delivering IT. This is a completely separate problem as we need to fix our protocols of interaction within technology existing inside a corporation that has a totally different goal. And that's a topic I can't answer quickly. Thank you. Okay, I think that's it. We're good.
Yeah, thank you, Martin.